I'm going to start with the same spreadsheet that I gave you. So you'll be starting at the same point. So this would be a good time to pull up your spreadsheet too if you're doing that. So the first problem is this singly constrained problem, and you're asked to fill in based on the information given in the worksheet, how to fill in the spreadsheet and solve for attractions. And remember, again, attractions is based on this concept of gravity, which in transportation, we love to borrow things from other fields or steal things from other fields. So we borrow things from physics and economics a lot. Most of the field of transportation planning is borrowed from those places. So this is a physics equation talking about how the size of two bodies have more attraction between them or more interaction between them. And the same thing can be said about locations. Two zones that are relatively large, that have large number of attractions and are fairly close together will have a higher amount of interaction than two smaller zones that are farther away. And so we're working on the same principle here. So let's go ahead and plug in the answers here for productions. And so I started you out with the idea of productions. And so this first set of 3 rows here, where I have 1 to 1, 1 to 2, and 1 to 3, we're talking about how do we take this 1,000 trips that come out of zone 1 and spread them across the 3 possible destinations, zones 1, 2, and 3. So in this case, I'm just going to copy and paste each one of these 3 formulas here, or 3 productions here. Because again, we're starting with, in this location, we're starting with the productions from all of, as you can see, all from 1 to 3. So it's all focused on what comes out of zone 1. And zone 1 has 1,000 productions. And so a couple of people I know got kind of tripped up by this because it's not intuitive that you would think that, that it would have 1,000 for each one of these rows. The place that it changes is when we start to talk about attractions. Now we're looking at the second part of this, right? So we're going from 1 to 1. And so the attractions in zone 1 is still 1,000, but now we're going on the next row from zone 1 and the attractions in zone 2. So this is our first step outside of our base zone. And so in this case, we're looking at zone 2 attractions, and zone 2 attractions are 1,500. In the third row, we're talking about trips that go from zone 1 to zone 3, and there are 200 attractions in zone 3. So right off the bat, it should be obvious that zone 3 is going to have the least attractions. It's both the farthest away from zone 1, and it has the least amount of attractions, the least things to do at the destination. So the fewest number of people are likely to go there. Now we have a distance calculation here. So we're just looking at the distance matrix that was provided. And again, this was all in miles. So the distance between zone 1 and 1, we just averaged at a half mile. And remember, when we talk about zones, the way the travel demand model works is it drops everything that's a local road that's inside a traffic analysis zone or transportation analysis zone. So anything inside a TAZ or a zone is ignored in the model because it's just too complicated. An actual software package that would be running a model just can't calculate all those local roads. So we have to stick to the major roads. So in terms of what the model sees, it sees a blank inside of a zone. And so we just hypothesize or average, what's the average distance from essentially the center of your zone to the nearest road that gets you on the larger network. So in this case, every zone internally is just going to have a half a mile. Okay. The second distance here is from zone 1 to zone 2, and that distance is 5 miles as given in the worksheet, And the distance between zone 1 and 3, remember this is the farthest one away, is 10. Okay. And then the speeds are also given 15 miles per hour. Again, that's pretty slow because that's just the kind of the average speed that someone would be driving from their house, maybe down a driveway on the local back road onto their bigger network. So it averages out at 15 miles an hour. Most common is about 25 miles per hour on the actual travel demand models that are used in Auckland and other places. We have 30 miles per hour as an average speed when traveling from zone 1 to 2. And from 1 to 3, we have 50 miles per hour. Okay, so this should be pretty straightforward. The travel time is pretty easy. So I already have the formula in here, but it's relatively straightforward. So it's just going to be the distance divided by speed, and that'll give you the distance. And then we multiply it by 60 to get it in miles per hour. And so on average, you go 2 miles per hour. Travel time is 2 minutes if you travel half a mile at 15 miles per hour. If you go 5 miles at 30 miles per hour, we can drag down the formula here. You get about 10 minutes and 12 minutes for going an average speed of 50 for 10 miles. So the travel time or speed between zones 1 and 3 are going to be pretty fast. Relatively, but they will take longer because of that extra distance. It's twice as far to from zone 1 to 3 than it is 1 to 2. Okay, and then terminal time. Now, a reminder what terminal time is. It's kind of a weird terminology, but terminal time is, as I kind of said in the lecture, is the amount of time it takes you, let's say when you're starting your trip, to leave your house, to get out your door, to get to your car. Maybe it's in the drive, maybe it's in a parking garage, maybe it's in some car park somewhere else, and it takes you a few minutes to get there. Maybe you're taking the bus or you're taking rail, so it's the amount of time it takes you to get to the rail station from your front door or to the bus stop. So that's the amount of time it takes you to get from kind of the real start of your journey, which is exiting your original location and getting to the first part of where you start on your transportation or your trip. On the back end, then it's however long it takes you to park your car and then get to your office or get inside the grocery store or get out of the transit station, etc. And so these are average times. And in a true model, we would have different travel times based on the location of the zone. So often locations in rural areas will have a different amount of time than urban, than a CBD. So CBD may be the longest if you're in a car, because you park the car and then it takes you quite a long time to park that car and then find, that it may be far away from your office. So you have to go through a parking garage, et cetera, et cetera. So there's a lot of different steps there. And so in a more complicated travel demand model, you're going to have terminal times that vary based on the location of the trip itself. And that may be different based on where you start your trip and where you end your trip. Okay. And so there would be a more complicated trip pattern or terminal time pattern associated with this. Turn off my notifications here. Okay. All right. So let's get back to the rest of this. So the terminal time, again, in this case, I gave you 2 minutes. And so it's going to be 2 minutes on both ends of the trip, no matter where you're going. So each trip carries an additional 4 minutes of travel time, okay, terminal time. When we get into the mode choice model, we'll get a little more complicated because we're going to start to use things like in-vehicle and out-of-vehicle time. And so we'll use a little more complex measure of travel times. Okay? Hopefully that makes sense to everybody. Okay, so we have 4 minutes additional travel time. And so when we start to look up our friction factors, and again, our friction factors are a little bit weird. They've always been called friction factors because that's kind of like the distance in gravity, right? There's friction in gravity. So we borrowed this term from physics again, but it really doesn't make sense in the way it's used in travel demand modeling because it's a conductivity factor. So the higher the number, the larger the number, the more activity there will be between two locations. So it's kind of the inverse of difficulty of travel. So the higher the travel time, the lower the friction factor. And this isn't just, and the reason we don't use just like the total travel time in this case is it's a more complex function that determines these numbers. So usually there's a substantial amount of work or research that goes into developing these tables. I just gave you a table, and it's a table that comes out of a pretty old textbook, a 1980s textbook. But these friction factors reflect not just the amount of time it takes to get from point A to point B as a conductivity factor, but it also takes into account the perception of time or the inconvenience. So substantial research has shown that for each minute that it takes you to get somewhere, each additional minute, it's incrementally or exponentially less attractive to you. So the difference between going from 1 minute to 2 minutes is substantially different. And then 2 minutes to 3 minutes, the exponent shrinks a little bit, or the difference in convenience or inconvenience shrinks a little bit, or perception. And so it's kind of not a straight line between travel time and your perception of how difficult it is to make that trip. When you get to, let's say, 20 minutes, adding 1 more minute isn't that big a difference. So it's a much higher friction or difficulty or inconvenience, perceived inconvenience at the lower end of the trip, where it may be the difference of a few minutes or 5 minutes. You're at 5 minutes and 6 minutes to travel somewhere. You're less likely to take that trip to somewhere else if it's an additional 1 or 2 minutes, if the whole trip is only 5 or 6 minutes, versus if you're going 20 minutes and there's an extra minute, you may go in that other direction. So it's a really complicated way of just figuring this out. But it's been an important factor in travel demand modeling and transportation modeling for a long time. So that's why I include it, because it's important to understand that kind of esoteric difference. So I gave you the first one just to give you a sense here. It's travel time plus terminal time. So your total trip time here is 6 minutes. I uploaded an image of the friction factors. I could have plugged them in there if I had extra time. I guess I could have plugged them in there to do a lookup table, but we'll just do it manually. So if we go to 6 minutes, we see it's 13149. So that's where that number comes from. I'll do these first ones, and then I'll just use my own cheat sheet to fill in the rest for 2 to 3 and etc. Or the origin of 2 and origin of 3. So the next one we look at, the travel time is 10 minutes to get from zone 1 to zone 2. And it's 4 minutes terminal time. So that's 14-minute trip time. Let's jump over to our friction factor table. So 14 minutes here. And we see that it's 4833. And so let me, of course, this is slightly on a different page for me. So that is 4833, okay? And then the last one here is 12 minutes of traveling and 4 minutes of terminal time. So that's 16 minutes. Jump over to 16 minutes. Look at that. And that's 3769. What happens if you get a weird number, which is possible, like let's say 16.5, or an average in between? In that case, you would take, so let's say 16.5, you would go over to your friction factor table and you would look at 16 and you would look at 17. You just take the average or add them together and divide by 2. And you could select kind of a friction factor that's in the middle of the two, or you could pick, it's fine if it's, if it's not exactly in the middle, if it's 16.3 or something like that, you could pick 16, just round down, or you could round up. The difference isn't that substantial that it'll make a huge difference, but generally, if you have a fraction, we take the average. So the last part here is to figure out the absolute attractiveness of the destination. So we have to figure out how likely is someone to go from, or what is the draw of a trip coming out of zone 1 and landing in zone 1, zone 2, and zone 3 based on how attractive it is and what that friction factor is, or that difficulty of travel is. Hit in the formula, which is attractions times friction factor for each zone pair. And so in this case, we get 13,149,000. And that number is completely meaningless. What we're looking for here is not the number itself, but the magnitude of this number relative to these other numbers. And that'll give us a fraction. Okay? And that fraction will be the percentage of trips that go from one zone to the other zones. So the next one is our 1,500 attractions. So a lot of attractions here times our friction factor. So 1,500 attractions in zone 2 times the friction factor between zone 1 and 2 of 4833, and that's 7 million, or almost a little more than half of what the attractiveness of zone 1 to 1 is to stay in that local zone. And then finally, the attractiveness of going all the way out to little old zone 3, which has barely any attractions, just 200 attractions, and a tiny friction factor or conductivity factor, whichever one you want to call it. And so we have 700,000, right? Not even cracking a million, okay? And then all we have to do is sum this up. So we hit sum, and we grab these values, okay? And in this case, the total is 21,152,300, okay? And then we have to figure out what the relative attractiveness is. And again, the relative attractiveness is the percentage of total attractiveness each zone holds. So that's pretty easy to do. We just have to divide each attractiveness, absolute attractiveness, by that total attractiveness number. So 13 million divided by 21 million, and that's about 62, right? 62% of all trips that go from zone 1 will go to zone 1 again. They'll stay there, okay? So the next one is, and we could use relative or absolute values here. In fact, I'll do that. So when you take 7 million divided by a little over 7 million divided by a little over 21 million, you get about 34%. And then for zone 3 here, it gets the leftover 4% of the trips. These should add up to 1, and we can just pull this summation over to make sure that we did it right. And that number is 1. If you don't get 1, something went wrong in this process here, okay? It should always add up to 1. Otherwise, you have too little, you've lost a slice of your pizza, or you have an extra slice in that pizza box, which is fine for pizza, but not so good for travel demand modeling, okay? All right, so now we just have to distribute those trips. That's simple enough. We just take the percentage of trips that are attracted, the relative attractiveness, and we multiply it by the productions, so the number of trips that come out of the zone. 622 trips between 1 and 2. We have 34% of that. Sorry, I was eating peanuts earlier, so I have a little peanut stuck in my throat. I'm not sick. So I have about 34% of trips come from that 1,000, excuse me, here. And so that's 343 trips. And then we have 4% of that 1,000 trips. So 0.04, the relative attractiveness times that 1,000. And that's 36 trips. And that should add up as well. So if we pull over this summation formula, that 1,000 is equal to productions. So your total TIJ, your total in this column, should always be equal to those productions. Again, if you have too many or too little, you've either added non-existent trips or you've lost some along the way. And then the last part here, this isn't really necessary. Actually, I just added it because it helps contribute to our understanding of why we have to do trip iterations. And so what I'm doing here, some of you got this, some of you just trying to drag numbers over. But what I'm saying is, this is the start of I just pointed my screen, and obviously you can't see that, but if where I have it dragging here, or this fake hand, what this is saying is the number of trips that are attracted from zone 1 here will say the first row to zone 1 as well. So this is kind of what we call a trip matrix, or the beginning of an interchange table. And so this is just going to be that 622. We're not going to put anything here because we don't have, because what we're trying to do is just kind of create this horizontal that shows us trips across from 1 to 2 to 3. So this is zone 2 coming from zone 1, and so that'll be that 343. And I don't want to confuse you with this. Again, this is not an extremely important part of this. It's just kind of more of the visualization to help you understand how this table is supposed to work. And then we have 36. Okay, so we have that straight across. So let me fill in quickly. I'm just going to quickly go through the last bit of this. So remember, we have 200 trips for zone 2 that come out of zone 2. So I'll just quickly do that, or try to do it quickly. This is going to be, so if you saw this is always going to be repetitive. We always have the same number of attractions because we're always going to go from a zone to zone 1 in the first row, zone 2 in the second row, zone 3 in the second row. So if you're kind of following that, not typing too much stuff, you could have figured out that you can just copy and paste this straight down. Distance is just a little bit reconfigured each time, but it's not too hard to figure out. Half a mile in between 2 and 2, 5 miles for 2 and 1, and we have 3 miles between 2 and 3. Is that right? Yeah. Yeah. Okay. And then we have speed. So 15, 15, and 40. Okay. And then the speed or the travel time, which again is just that formula, distance divided by speed times 60. And then the terminal time, which is the same for every zone. Okay. Again, if I'm going too fast or something needs to be explained, let me know. Using these friction factors, that's 24 minutes here. So it's 1379, 131, 49. Here I'm just using my cheat sheet instead of going back and forth from the friction factors, but I'm just pulling these over from the friction factors here, the friction factor table. And then 9620. 9620. Okay. All right. So now that we have that, I'm just going to copy and paste my formulas straight over all the way across. I'm going to take everything here, but this will be wrong. So let me just pull this over here. There we go. Because that was an absolute reference. And I'll paste my formulas. Okay. So that adds to 1. So now you see that, again, this is another case where a lot of times, as I talked about earlier, the travel inside a zone is discarded altogether from a 4-step model. Here we've included it just because it's easier than kind of zeroing it out and adding extra zones. So as a result, though, there'll be the most travel that will occur is internally. A zone will be most attracted to itself because of that low distance and the high number of jobs between the two of them. So that's the reason for kind of a significant amount of travel in between those two zones. Okay, and then I'm going to do the same thing with this last one, but this is going to be 1,500 trips because we're talking about zone 3. Zone 3 produces 1,500 the whole time. 10, 3, and 0.5 for our distances. Our speeds are 30, 40, and 25. Okay. And then we have our travel time, which is, again, just that formula. So I'll just drag that down. And then our terminal time. Okay. And then our friction factors here, again, 1379. We've seen that number before. For friction factor here, 9620. And 14,924. Okay. All right. So those are our friction factors. We'll just pull these formulas in one more time. Okay. And fix this formula here. There we go. when we do this, what we have here are the correct trips between each zone, but they're not exactly distributed in the right way. They don't represent the attractions. So if you look here, the productions are correct, Tij, in each case. But the way that we created this distribution, if you look at the attractions to zone 1, which would be everything in this column, you can sum them up. And if you hit sum, and you just sum up, oops, you have to actually hit the equal sign. If you hit sum and you pull in all these numbers, what you'll see is 744 trips. That means based on this model or this iteration, first, cut at trip distribution, you have the right number of productions, but the number of trips attracted to zone 1 says it is only 744, when there should be 1,000 trips attracted to zone 1. And if we pull this over, it also overestimates the number of trips attracted to zone 2. It says there'd be 1,666 when there should only be 1,500, and 291 to zone 3 when there should only be 200. So by using this method in one iteration, we're not very close, or we've gotten off in the number of productions and attractions we should have. Now, what do we do if there's a speed change? And so I'm going to take the lazy person approach here, and I'm just going to copy all my data that I have in here. Literally just copy it and paste it into the spreadsheet. That's why I made them exactly the same. If you didn't notice that, they're line for line identical, so they can just be pasted in there. Okay. So now we have the original problem here duplicated on this spreadsheet. Sorry if I'm bouncing back and forth, it's nauseating you. But we just have to adjust the speed now. So we know that what happens is between links 1 and 2 in the hypothetical links 1 and 2, we change the speed. So there's a speed improvement of 70 miles per hour. So we just pop in the new speed here. This is a really simple question, but it can trip you up if you're not reading it carefully. So 1 and 2 and 1 and 3. I didn't say that there would be a speed change between 2 and 1 and 3 and 1. Some of you did it, and I think that's a fair thing to do. So I'm going to go ahead and change it as well. It's fine to assume that reverse trip would also be 70 miles an hour. It'd be weird if just one side of the road was 70 and the other side was 30. It seems kind of dangerous. So we'll make the safer speed adjustment here. Okay. And so what happens here is there's not a significant change, but what happens here is there's a slight increase in the number of trips on average, or there should be. So we have a decrease in the number of trips. So what we have to do is go back to our lookup table. And this is where that question that I answered that nobody actually asks comes in, because now we have a partial time. So in this case, we have 4.2 plus 4, so 8.2. And we can round that one down. So 8.2 on the friction factor here. We can just round that down to 8. So that's 10,222. Okay. So in this case, it's now 10,222. Okay. And in this case here, we could either round it to the nearest number, or we could take the average of the two. So we have 8 plus 4. Right, so 12.5, and then it's almost 12.6. So just for our speed here, we could say that that's maybe 13. And you could, again, take the average between 12 and 13 and do it that way. I'm just going to say it's 13, just so we can get through this and get to the last portion here before I run out of time. So now the conductivity here, or the friction factor, increases, which means there'll be more travel between these two zones. And then as a result, the relative attractiveness of everything changes a little bit, or the absolute attractiveness changes, which changes the relative attractiveness. And so this goes down from 62% of all the trips in relative attractiveness to 44. and zone 1 and 2 picks up a lot more trips as a result, and we don't have too much of a change for zone 1 to 3, but we get a little bit of a change, right? So it gets one more trip. So that's how it changes. So those speed differences, and if I carried this through, I won't carry it through here, but if I did the new friction factors here, you would see the change, or I guess I can because it's just 10. It's just these changes here. There we go. Okay, so those are the changes. So now we have a redistribution of those trips. Okay, does that make sense to everybody? Hopefully. Okay, so that's all we're doing is just changing the average speed essentially between those two locations. All right, so now let's jump into the kind of the more complicated portion here, which is the iterations. So I'm going to do the same thing here. You know, I'm a big believer in don't reinvent the wheel or don't do things twice you've already done. So I'm just going to paste in, and hopefully you can do the same thing as well if you have this already set up. I'm just pasting all the data that I had in my first part of the problem, problem 1, singly constrained, and pasting it into problem 3, iteration 1. And this is the first iteration, so this is the first cut at this. And again, just to remind you, so what's wrong here is that the attractions in zone 1 to zone 1 are just based on the number of productions that come out of zone 1 and the relative attractiveness of that zone. So it doesn't actually add up perfectly to the 1,000 attractions that are actually in zone 1 or the 1,500 attractions in zone 2. It's just an approximation. And so we're going to go through a couple iterations so that we can get that correct. So what we want to know here is through this iterative process is how far off from our actual trip count are we, right? So what percentage is this number off from the actual attractions? And so one way we could do that is just to take the actual attractions. So we have this equal sign here, and we take the number of attractions, that's 1,000, and divide it by what we came up with, that's 744. And so we get 1.344. And what that means is that we undercounted our attractions to zone 1 by about 34%, okay? And so we can do the same thing with the next one. We take our 1,500 trips and we divide it by, because this is zone 2 we're looking at here in this column, divide it by our 1,600. And what that means is we overcounted our trips here by about 10%, right? So that says 90. And so this is the amount that we're going to have to round down. Okay. And then the last part here is how many trips do we over or under count that are attracted to zone 3? We take 200 and we divide that by 291. Okay, we overestimated by a significant amount, about 32%, or 42%, sorry. Oh no, sorry, it is 32%. I didn't see that, 8. So about 32% is what we overestimated those trips. So we can fix that by kind of going through this process a couple of times. And the way that we do that is we can jump to a second iteration. And in a second iteration, so what I'm going to do is I'm just going to copy all of this again. Again, this is just a lot of copying and pasting. We could programmatically do this through scripts and other things like this, but just for the sake of simplicity, we're just going to copy and paste. So we're going to go to iteration 2 here, and we're going to paste all that information in there. Oops, I didn't do that. Let me try that again. I'm going to paste all that information we just put together here. Okay. In here. Okay. And then we're going to have a second iteration. And so to figure out this number, first we're going to say, what are the given attractions? That's fine. But what we're going to say here is how many attractions should we change this to or re-weight this to based on our over or under count, right? And so this is where it gets a little bit complicated. But we're essentially going to say this number is equal to the 1,000 trips that are actually attracted to zone 1 times what the difference or the undercount in our model, which is 34%. And when we do that, it tells us that, we undercounted, and if we wanted to try to weight this model so that it bumps up that factor a little bit, or overweights the attractions so that it can resemble the real attractiveness for that location based on our data better, we should use a number of attractions that is actually closer to 1,344. Okay, and then we're going to do the same thing for zone 2, which is, again, multiplying the actual number of attractions times the over or under count here. And that means we'll have 1,351. So that kind of brings down the attractions, or will make it seem relatively less attractive. Okay. Again, this is a little complicated. This isn't super critical. So if you're kind of get lost, let me know, but don't feel like you absolutely have to know this stuff. This is just so you can kind of get a sense of this process that the software goes through when it does this sort of calculation. So the last one, we're going to look at the actual attractions, and we're going to multiply that by the under or over count here. And what we'll say is, in a spreadsheet, it should actually look like 137 to get closer to that number. And then the last step here is we're going to replace these numbers with the ones we've just calculated so that we can change or adjust the relative attractiveness of each one of these. And so this is going to be equal to this number, and then we'll drag it down. Okay. And then I'm just going to copy and paste these values. Actually, I'm going to do it. Never mind. I'm going to do it so it's the same in each one of these. So I'm just copying these all the way through, so changing all the attractions. And hopefully what you're seeing here is that these numbers are starting to get closer to the actual numbers. Now we went from 700 something to 800, or almost 900. So we're getting closer to that 1,000 that's in the original number here, that 1,000. Now we're at 1,500. So we went from 1,666 to 1,587. So we're getting lower. And this is also getting lower, closer to the 200. And so we can replicate this whole process again. So I'm just going to take all these numbers, copy them again, and go to a third iteration. X. And this one I didn't include anything, so I'm just going to copy everything here. Otherwise it'll be messy. There we go. I'm going to copy this whole worksheet essentially over to a third iteration. Okay. And I'll let you do the last two iterations, but I'll show you how we get closer here for the last one. Okay. And so this one here, we're just going to base it off of our previous iteration. And so what you're seeing here is, or should be seen here, is these numbers are should be getting a little bit closer. We should actually have this over here. No, okay, so it's getting a little bit closer to the actual level of productions and attractions. That's 9.4, and this is this here. Okay, all right. So these are getting a little closer in the third iteration, or by the third iteration, or by the second iteration, they're getting a little bit closer. Sorry, I'm kind of making this a little more complicated than I thought. The wrong thing there. There we go. And so in this next iteration, we're going to kind of do the exact same thing. It's just going to look at the numbers from the last one, so equals, and then we're going to say, what's the number based on the last set of iterations times our previous number, and so it'll be 1498 is what those should look like. So it's bumping them up, and this one's going to be equal to how much we are off in zone 2. Okay. Times what we had in the previous iteration, and then the last formula here will be equal to, and then when you paste this again, it'll actually be the right location. I just hit the wrong formula at first. Okay, times 92. Okay, and so oops, that's not right. Sorry, I got this number wrong here. Goodness. This is what happens when you work late at night. Okay, so this is just actually equal to this divided by the actual one. Oops, the actual one divided by this. There we go. Okay, there we are. Okay, so so when you get that in, you'll be getting a little bit closer to your actual iterations. This one wrong. Sorry. There we go. There you go. Okay. So you're getting, these numbers are getting a little bit closer. Eventually they'll get to be like 9999 or whatever else, and get a little bit closer. But in this case, what you see here is these numbers again are a bit closer to what they should be. This is closer to 200, are getting closer to 200. This is getting closer to 1500. This is getting closer to 900. So again, you would go through this step a few times until by iteration 5, you're basically at the point where you have the equal number of attractions in your trip distribution process as you did in the modeled data set. Okay, so that, I know that was probably not the clearest explanation of this process, but that's the process you go through to kind of doubly constrain. So a singly constrained model is you're simply constraining all those trip distributions based on your known productions in each zone, and doubly constraining it is that distribution is being locked in by both known values, both the productions and attractions. And since we created a balanced productions and attractions table in the previous trip generation, we assume now that the attractions are an accurate count or accurately reflect the number of opportunities or things that people are attracted to in the destination zone.